Okay, so here's an example of a problem that's using density. So this is 15.4, problem number 2, and we're going to set up a double integral over some region to figure out what the charge density is over that region. So charge density is the same idea that we use to talk about mass, that we're going to take the function. The function describes how the charge is changing over the region, and we're going to do the double integral over that region to find out what the total charge is. So doing this, the first thing that we should look at is what is the region that we're operating with. So this is my region. So a quick sketch of that region. This is a unit circle, or the unit disk, sorry. So maybe what I didn't mention or wasn't clear when we talked about polar coordinates and double integrals is that this region that I'm integrating over is what's determining if I'm using rectangular coordinates or if I'm going to use polar coordinates. So looking here, rectangular coordinates, I can have x values go from -1 to +1, and then I can bound my y values with the square root of 1 minus x squared and the negative square root of 1 minus x squared. Instead of doing that, that's going to lead to integrals that are going to be more difficult. Instead, what I'm going to do is I'm going to use polar, because now I can take my radius is going to be anything from 0 to 1. And then my angles are going to go between 0 and 2 pi. So again, we said that any circle centered at the origin is considered a polar rectangle if I use polar coordinates. So I'm going to go ahead and take those to be the bounds now. So then that means that I want to rewrite my function. Instead of having my function be in terms of x's and y's, I want to rewrite this in terms of r and theta. But I know in polar that x squared plus y squared is just my radius squared. So that means that this is going to be the square root of r squared, which is just r. So I'm going to write this is just my general formula to find the total charge density. I'm going to write this as the integral. Theta goes from 0 to 2 pi. My radius goes from 0 to 1. And I said you can put little variables here to remind you which each one stands for. My function is just r. I'm going to multiply that by r dr d theta. So when I'm switching from a rectangular situation into a polar coordinates, I need to make sure that I include this. Don't forget that r. So now what I'm going to do is I'm going to take this, I'm going to separate the two integrals. Since I have nothing in terms of theta here, that means that this whole integral will just become a coefficient. So I can integrate from 0 to 2 pi d theta, and then I can integrate from 0 to 1 r squared. So now here, antiderivative is just going to be theta. So I have 2 pi minus 0. That's going to give me 2 pi. Here, my antiderivative is going to be 1/3 r cubed. So that's going to give me 1/3 minus 0. Giving me the total charge over my region is going to be 2 pi over 3. Units, sorry. Coulombs. You might not know what the units are for these things. That's why in the problem, if you go back to the description, it tells you what the units are. The charge density is given as coulombs per meter squared, and that our units are as meters. So when I integrate over the x and y, or r and theta, the per meter squared is going to cancel out, and I'm just left with the electricity, which is coulombs. All right, so there's an example, kind of reviewing polar coordinates, how we switch from rectangular to polar, how I can separate my integral into two different integrals that are getting multiplied together, antiderivatives, an answer. If you have any questions, please post them on the discussion board or send me an email. If you want some more examples, I will go ahead and post number 6 and number 18. Those have moments of inertia and then moments in center of mass. A little warning ahead of time, when you're doing those, they are very computational heavy. So you gotta make sure that you're being very careful and very diligent about organizing your work and going through step by step slowly. Okay, so in the future, look for those. Thank you much. Have a great day.